Yeah. It's just, it's a privilege. It's exciting. It's sort of wonderful. This is a wonderful conference. It's just, I wanted to say something about Paul. I don't know Paul as well as I might. We've never really been in the same place much. I have the impression that he's somebody who's very clear-sighted, sort of sees very deeply into things. I was thinking about Hans Werner's remarks yesterday about Paul being sort of unflappable. And it occurred to me there's this old joke about the guy who can walk in the rain and not get wet because he walks between the raindrops. And I sort of think of Paul as someone like that. And the other image that occurred to me about Paul is these astronomical bodies that are very hard to see because they pump out an enormous amount of energy, but it's all in the ultraviolet. I'm going to try to give this talk about an analogy and make this sort of claim. So I've put it up here as an analogy, and then I realized later, so here's an analogy. These analogies are very ancient, right? They go back to the Greeks or something like that. It occurred to me that people who they do, like Eudoxus's theory of areas or something like that. It occurred to me that people used to thinking about higher category theory might sort of alternately express this kind of, what I'm trying to say up here, as a kind of a push-out. Or, sort of here's some one morphisms and here's a two morphism. And what I'm trying to say is, everybody, it's a sort of known fact that the greatest period in mathematics was when you were in grad school. And when I was in grad school, the sort of understanding of differential topology in terms of arithmetic structures was just this enormous sort of like a nova in the sky or something like that. The Adams conjecture, the stuff about the image of J. The image of J also relates to the co-kernel of J, and I sort of think it's useful to remind people that the co-kernel of J is the major part of the group of differentiable structures on the spheres. I think people tend to forget that. And then there are these other sort of contexts like Sullivan's work on the classifying space for PL structures, which turns out to involve, in a profound way, the structure of the maximal abelian extension of the rationals. So, on the other hand, also in this, a little bit before that, in the 60s, there was an enormous expansion in number theory of work by Artin, Sayre, Lubin-Tate, people like that. And I want to make an argument that chromatic homotopy theory is the sort of push-out of those two sets of ideas, one from geometry and one from number theory. So this is an analogy, and analogies break down. You could always, if it's a good analogy, it might be sort of good down to codimension 3 or 4 or something like that, but then in codimension 5 you'll find some obstruction or something. So I want to sort of push this using ideas, new ideas from topological Hochschild homology that I learned about from Lars Hesselholt, but also involve a lot of new work by Peter Schultz and people around them. So, and I'm not an expert in this, and I'm certainly not an expert in THH either. So this is part of this is a report on my attempts to sort of learn some of this stuff and wonder how things that come out of this side of this way of thinking about things might fit together with stuff that come up in chromatic homotopy theory. So actually, mostly what I want to say is, I mean, most of what this talk is going to be about is some way of thinking of some analog of the Dennis trace as something like a Chern character for these sort of higher K theories, or these extraordinary K theories, or whatever. Okay, so I've tried to summarize here some work of Arola, some work of Hesselholt on the algebraic K theory of the p-adic complex numbers. Now, there's going to be a lot of number theory in this talk. It's not going to be that exotic, I hope, but it's maybe not very standard. I mean, if you happen not to be deeply involved in that. So I put a kind of a glossary of terms over here, which will recur in this document, in these slides. I apologize for these sort of, this is like steampunk technology for you guys, but it's the best I can do. Okay, so, well, there's this thing called the p-adic complex numbers, and they're algebraically isomorphic to the ordinary complex numbers. I'll say more about them in a second. But and it's sort of known from Suslin that the algebraic K theory, I put a small k here because this is non-periodic, right? It's not going to be periodic for a while. With p-adic coefficients is isomorphic to the p-adic completion of ordinary K theory. Ordinary to me means that here it's a complex K theory. So here you get this polynomial ring on degree 2, the generator being the bot class. And there's this trace map to topological Hochschild homology, also p-adically completed, which I'm going to denote in these slides by a boldface T, okay? Because otherwise I just sort of can't fit some of the diagrams on the slides. So that's just an expedient. I hope nobody will mind. And there's this trace map called the Dennis trace from K theory to THH. And that's part of this whole system of stuff that people interested in cyclic homology study. Topological cyclic homology. So there's THH, which I'm writing as boldface T, and according to Madsen and Hesselholt, that's just the beginning of a sort of a tower of complicated structures with cyclic group actions, which I forgot to write here, is part of what this structure is called the sort of big de Rham-Witt complex, de Rham-Witt complex. And in this, in what I have to say today, that's not going to occur. I'm only going to be talking about THH. But for them, that's sort of the point of all of this business. So what's going on? The interesting thing in this picture, okay, so there are these p-adic complex numbers. They have a valuation ring, a ring of integers. And this map down here is the inclusion of the p-adic integers into the valuation ring of the complex numbers. This is a polynomial on one generator. This is polynomial on one generator. The bot class goes to a certain class P0 times the generator over here. And P0 is that thing. For example, this I cite it now because it's going to be a sort of persistent player in what comes next. Okay, so that's what I just said. Oh, I also should say that these p-adic completions are one of the things Hesselholt and Madsen introduced into the subject, and they're a great idea because a lot of these THH groups are things like, you know, huge torsion groups in odd degrees, and once you p-adically complete them, they jump over into even degrees and tend to be nice free p-adic modules and things like that, and they sort of simplify your understanding enormously, or at least if you're me. And these THH things, one of the reasons they're nice is that they're generalized under McLean spectrum, and so spectra for classical rings, and so for many purposes, they're sort of familiar looking and accessible. And then, so here I said some, trying to say something about how I want to make Chern characters out of this stuff. Okay, so here's a little bit of explanation about this field of p-adic complex numbers. So it's rather more complicated than the usual construction of C. You take your p-adic field of p-adic rationals, take an algebraic closure, and then you complete it. And what you get is, I was very tempted to write in this with the other spelling just to be salacious, but I restrained myself. So there's a sort of order map, so the deal about CP, the p-adic numbers, is that it contains all the, rational powers of P, and there's an order homomorphism that takes a multiplicative group, sends, P to the R to R. So I'm later going to be talking about these things called perfectoid fields. And basically, perfectoid fields are sort of like p-adic fields. They're complete, and they contain all possible roots of P. They're just ramified all to hell. And the moral of the story is that once you pass to that limit, some things become simpler. So in particular, this guy, P0, has P order 1 over P minus 1. So when P is equal to 2, it has 1. And it's minus 2. Okay, so now this field it has a valuation, so it has a valuation ring of elements of non-negative order that has a maximal ideal. The quotient of the big field of the local ring by the maximal ideal, in this case for CP, is algebraically closed. So this is like a field which has a valuation ring. The field is algebraically closed. The residue ring is also algebraically closed. So those guys, so here's CP over here. It's the completion of QP, and then there's some other guys in here which I'll describe in a second. Now, there's this thing called Lefschetz's principle in algebraic geometry that says that if you're going to do your algebraic geometry over an algebraically closed field of characteristic 0, it shouldn't matter what your algebraically closed field is. That they should all be effectively the same geometrically. On the other hand, these fields have lots of sort of arithmetic properties. This field like CP has an enormous action of the Galois group on it, which you don't see classically. Classically, you just see the complex numbers over the reals. You see plus or minus 1. And it has other interesting features. One of the things that I remember is Matt Ando telling me once that there was this thing of Eisenstein. Eisenstein says, okay, well, we have C mod Z2 and we get all these beautiful elliptic curves. Why can't we do that? And we can't do that because these things are sort of dense in here. But in the case of whatever you put down here, these things are sort of just totally disconnected, and there's a lot more room, and there are these sort of analogs, these sort of group objects in that category for us to play with. So there are lots of interesting things in this geometry over CP that haven't really, I think are sort of new to us. On the other hand, there's geometric things that we don't know how to do over CP, like cobordism, until talk yesterday about MGL spectra, which sounded very exciting, but maybe that's out of place here. So anyway, those are some big fields, CP and QP and things like that. Now, On the other hand, if you start closer to the bottom, with QP, you can look at finite extensions of QP, and those are local number fields. That's a kind of a pun because they have associated local rings, and they're also locally compact topologically. So you have these finite extensions of QP, and they have some structure which you can sort of summarize quickly. So you have this local field, it has a valuation ring. That valuation ring has a maximal ideal, which is principal, which has this sort of generating element pi, which is a generalization of p for the cases of p-adic integers. The quotient field is finite with p to the f elements, and the order of this element pi is an integer called e, which is called the ramification index. I'm sorry, that should be e inverse, and e times f is the order of the field extension. So that's your mini course in algebraic number theory, local algebraic number theory for the moment. So one of these things that happened in this sort of 60s revolution in number theory was the invention of these things called Lubin-Tate groups, which associate to such a local field a formal group law. The formal group law is essentially unique. I don't want to sort of go into the delicacies of that. But according to Quillen, the formal group law defines a homomorphism. So these, the Lubin-Tate theory associates to a field. I'm going to come back to this. A formal group law over the ring of integers of the field, and it's classified by a map from MU. To make things graded, I put in a degree 2 indeterminate to carry the grading here. And I want to call that the Hirzebruch L genus, which is a pun, another pun, because Hirzebruch defined the L genus as and that's something completely different. It's the function which assigns to a manifold its signature. But here we have these local fields L, and we've got one of these genuses for each L. And I sent an email to Hirzebruch about this, but he hasn't responded yet. So, and so I want to know if we can connect this this formal group stuff somehow with the geometry over these kind of fields, and make some, one of the things you encounter if you're working in chromatic homotopy theory is people say, well, what good is it? I mean, you encounter this in lots of parts of mathematics. But in chromatic homotopy theory, it'd be nice to point to sort of geometric things that one can understand in other terms. And I'm propagandizing that geometry is going to be found in sort of arithmetic geometric constructions that involve a lot of ramification. That the unramified stuff is seen in the image of J, but that once you start hitting ramification, that you need to move to some kind of higher chromatic level. And as an aside to that, it's sort of peripheral, but I just want to make a sort of general remark that it's a sort of fact of life that E-infinity ring structures don't play well with ramification. Right? They play well with étale things, but once you see ramification, things get complicated. And those things are in some sense accessible because through work of Hopkins and Gorse and things like that, but it's sort of unfamiliar territory at the moment. Okay, now, so algebraic topologists talk a lot about formal groups, but they don't make much use of, and number theorists also talk a lot about formal groups, but algebraic topologists don't seem to make much use of what the number theorists invented the subject for. Okay, so what the algebraic geometers, algebraic number theorists said, okay, so given a local field L it has a Lubin-Tate group, and you can look at its group of points, which is what you do when you take the maximal ideal of Cp, this algebraically closed thing, and add them with respect to the formal group law. And because that thing is complete, you get an honest group object. That group object turns out to be, if the field has height n, I should have written this down, that turns out to be something like n copies of Q mod Zp plus an infinite dimensional rational vector space. So it's really something like an n-dimensional torus or something like that. And so those elements, the elements in that subgroup are called the torsion points of the Lubin-Tate group. And if you take those points and adjoin them to the field L, you get this thing called, so there's in the, in the subject, there doesn't, this field L infinity, it's the maximal sorry, I have clumsy thumbs. It's the maximal totally ramified abelian extension. There's a maximal unramified abelian extension, which is another thing, which I'm not going to be talking about. Anyway, there's no obvious notation for this except that Peter Schneider and Munster has a very nice set of notes on this subject on his webpage, which I recommend, which talks about a lot about these kind of things. And he uses this notation where you put infinity up here. So this is not the maximal abelian extension, it's the maximal totally ramified abelian extension with all these roots of p. Okay, so and that's the thing that you get by adjoining all these torsion elements on the Lubin-Tate group. If your field is Qp, then the Lubin-Tate group is just the multiplicative group, and you're just adjoining the p-power roots of unity. And that's this field over here, which I'm denoting by Qp infinity. Otherwise, so here you have a local field. Here's L infinity with all these Lubin-Tate points adjoined. Here's Qp, which has precisely the roots of unity. And these fields have completions, which are perfectoid. And I put a p here to indicate that there might be some other perfectoid field, some generic perfectoid field that I want to talk about. So those are the players in the number theory story. One of the reasons one is interested in this, these extensions is one has perfect control of their Galois theory, at least the behavior of L infinity over L is just strictly, it's isomorphic to the multiplicative group of the roots of, the multiplicative group of the valuation ring. So P, in the case of Qp infinity, that would be Zp cross on the left, and that's the stuff that comes up in Kronecker-Weber theory. Are you guys okay? Okay. So, so when you complete these things, when you complete these fields that have all these roots of unity in it, and then you get you, roughly speaking, get perfectoid fields. And from as far as this talk is concerned, that's going to be sort of a rough definition of what a perfectoid field is. Perfectoid fields are sort of very geometric, and these particular things that you get from Lubin-Tate theory, I think, should be thought of as sort of generalized cyclotomic fields. And I want to make propaganda that they're very natural places to try to do sort of classical-looking geometry. Even though these fields, the CP is a sort of an exotic place to work for now. Okay, so here's what I'm claiming in this talk, is that, first of all, this is, I'm basing this on work of Schulze-Batt and Morrow, that THH of these rings with p-adic coefficients are polynomial in a degree 2 generator over this ring itself. and that they're orientable, they're complex orientable, and that the formal group law one can identify turns out to be something which is already known in a sort of different guise. It's a kind of an analog of the Lubin-Tate group in a different category, in the category of rigid analytic objects. So rigid analytic geometry is the subject that I sort of carefully avoided for 30 years. But now I find out, I mean, you know, mathematics is very non-Hausdorff. The closure of something involves you in all kinds of other things. And that the classifying homomorphism for this formal group law factors through this thing that I call the Hirzebruch L genus, which is gives you a formal group law of height n over the residue field. Okay, so it's the thing that I think is interesting is not so much. Well, I mean, it's actually quite interesting that these things. I don't know what that little hand is doing. I'm sorry. It's just. It's interesting enough that you can classify this formal group law, I guess. But what's really interesting is its connection with Lubin-Tate theory. And so I claim this is compatible with Artin reciprocity. I said Artin reciprocity instead of Galois equivariant because these things have something to do with what these sort of hypothetical integral lifts of the Kn theories. And one might think of operations here as being like generalized Adams operations. And those operations act linearly on here. On the other hand, the Galois group of these fields acts on these guys naturally. And the action here is linear. The action here is semilinear. And the action here acts on this generator by multiplying by a unit of this ring OL, whereas the action here acts on this thing semilinearly, so it twists the coefficients around, but it acts on the generator only by multiplication by a p-adic unit, something in ZP cross. So at first sight, these actions look very different, and reconciling them is really what the technical part of this talk. Okay, that's the real point of what I'm hoping to say. So I want to say a little bit about where this complex orientation comes from in classical terms. So if you look at this field Qp with all the roots of unity, p-power roots of unity adjoined, you can make an analog of the Hopf line, and it lives in the K-theory of this field with coefficients in classifying space for the group of units in the field. And that's, I claim, a good sort of natural analog of the Hopf line in the algebraic K-theory of CP.
What's mu in that slide?
My
It beat mu. What is mu?
mu is the p-power roots of unity. Or really better, it ought to just be the multiplicative group of the field, because I'm going to shift it back and forth. So you can think of it's the analog in this context of CP infinity. It's the analog of classifying space of the circle group. They're pretty much the same once you p-adically complete everything.
Jack, when a perfectoid field is interesting, at each level of the inverse limit, is it typically uncountable?
Is it typically
Uncountable. So it's discrete, is it typically uncountable?
Yes. Yeah. Um, oh, so so I want to build this thing over Qp infinity. But then I want to push it down into Cp, where it's very close on, it sort of essentially is the Hopf line p-adically. And so the algebraic K-theory of this guy is what you expect. It's K, connective K of Cp infinity in this guy that I've called eta tilde, which is basically the Chern class of the line bundle in K-theory. So that's my coordinate for the formal group over K of Cp, and because of that multiplicativity of the thing I called eta p on the previous slide, so this guy is reduced. This eta tilde is reduced, and it's shifted up in degree. So we get this guy here whose diagonal looks like this with beta p here to compensate for the degree change, and that's the sort of classical diagonal that you see in K-theory of Cp infinity, classical K-theory of Cp infinity. So now I claim that if we take, I guess the diagram I want here is here. That if you take the algebraic K-theory of Cp of Qp infinity, map it to the algebraic K-theory of Cp, and then look at the analog of the Dennis trace down to these fields here, by this theorem of Schulze and Watt and company, these guys are going to be polynomial rings in these degrees, and this eta guy is going to map down to the image of these corresponding things in these Tate homology groups. I'm sorry. I wanted to go back. Or maybe it's better to go forward. So you have these guys here, which are the coordinates in THH of B mu, can be written, if you sort of, in terms of the Chern class, in the classical Chern class, by a formula like this. Remember that the relation between the Chern class in K-theory and the Chern class in homology is given by an exponential. And here you have an exponential, but the key fact here is the presence of these p zeros here, which go back to Hesselholz's theorem that was on the first page of this slide. So in particular, the diagonal for these guys is very much like the diagonal that we had for K-theory, but there's a p0 here, right? This gamma q is an element of degree 2 to make the degrees balance out. Now, maybe this is time for the quiz. Okay. So here's the exercise. And the quiz question is, has anybody ever seen this formula before? It says that 1/2 e to the 2x minus 1 is congruent to the sum of x to the 2n for x to the 2 to the n for all positive n. And if you invert it, there's a similar formula, I guess, for Bernoulli numbers or something, which I couldn't quite figure out. Anyway, the thing is that if you just sort of write it out, you see that this 2 in the numerator kills all the powers of all the 2's that appear in the factorial denominators in the exponential function, and you get this series that has 2 radically integral coefficients. And so more generally, if you take this guy P0, where did I put him? Well, anyway, if you take this guy P0, which satisfies this funny relation, and you look at this sort of twisted version of the exponential, then you get something in the integers of the field Qp with this P0, with this P minus first root of P adjoined. And if you sort of write this out, okay, you get this P0 to the n minus 1 times x to the n over n factorial. But then if you look at the P order of this contraption here, P naught has P order 1 has P order 1 over P minus 1. It occurs n minus 1 times. On the other hand, there's a theorem of Legendre that evaluates the P order of n factorial as this thing, where alpha sub P is the sum of the terms in the p-adic expansion of the integer. And it turns out, so this alpha P is always greater than or equal to 1 if n is greater than or equal to 1, because there's going to be some integer in the p-adic expansion. So that thing, that series is p-adically integral. So this provides a sort of an analog of the Dennis trace, which I haven't ever seen. So if you make a sort of fake version of the Chern class, where you put a P0 in there, that beta is the bot element, just to sort of straighten out the degrees, and you think of that as a symmetric function, think of it as defining a characteristic class, you get a version of the Chern character, or something like the Chern character, that goes from connective K-theory to cohomology with sort of p-integral coefficients. And the thing is that if you evaluate this on the bot class, then this trace on the bot class gives you P naught times the generator on the 2-sphere. This is just like Hesselhold's theorem. And that's not integral, right? So this is not a coordinate for the formal group. So, but if you invert beta, then you're effectively inverting P0. So if you invert beta, you get something that goes into something with rational coefficients, characteristic zero field coefficients, which is basically just the classical Chern character. So this is a sort of a version over the complex numbers of what Hesselhold's theorem says for the p-adic complex numbers. Okay, now I want to tell you a sort of a secret that I don't think the arithmetic guys know about Lubin-Tate groups. And it's a sort of simple general theorem, so I'm going to switch topics now, okay? If you have a Lubin-Tate group for field L, you can take it to be of this form. That's an old theorem of Honda. It's very beautiful. It doesn't have there's some choices involved, and for other things, you might want to make other choices. But I'm going to say, for the moment, I want to look at this kind of thing. And I want to generalize what happened on the previous slides by looking at well, it's at this stage it's convenient to look at the logarithm instead of the exponential, but they're inverse, so it's essentially the same story. So if you take the logarithm and twist it the same way, but you use an element pi 0, I'm not sure where the...
Is pi the uniformizer, or is pi just any other element?
No, pi, yeah, pi, that's, it satisfies the same equation. So this is the unified, so it's a q, remember q is p to the f. It's the analog of p0 for the uniformizer, but I'm using q instead of p. I'm using f in that thing. How did I get to this slide? I claim that if you do this, that this thing has integral coefficients. And so this is pretty much the same kind of argument, only simpler, because the Honda's logarithm is what people call p-typical. So if you write it out, you get pi naught to the q to the n minus 1, and you look at the p order of this guy, and you get E inverse, and then you get q to the n minus 1 over q. And this is, this Gaussian factorial or something like that. And it's always, this is 1 plus q squared, blah, 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 minus n, which is non-negative. And so, in fact, the order here goes to infinity, as n does, which is a definition of a rigid analytic function. So if you've done this trick to the logarithm, you get a formal group. You can translate the formal group by something like this, which has a logarithm which is integral. Therefore, it's a logarithm. The formal group is of additive type. It's isomorphic to the additive group. Okay, now I'm running out of time. One reason I wrote these slides up in such detail was so that I would have a hard copy that I could distribute to people who wanted to see more details. So I wrote in, there's a version of this with much more detail. I mean, not much more detail, but there's a version of this, and I'll be happy to send it. So the thing is that, now we're working with, so I'm going to go fast and skip some stuff, but now we're working with formal group laws over graded rings. And one of the things I want to say is that, that you can think of this additive version of the formal group as coming from the Lubin-Tate group, where you pull it back by a map which on the degree 2 polynomial generator multiplies by pi 0. Okay, so that's not what people normally regard as a morphism of formal groups, right? A morphism of formal groups stays over the same base ring and changes the coordinates. I'm talking about taking a formal group over some ring and changing the base ring by multiplying the polynomial generator by this pi 0 guy, and I claim that this additivizes its formal group law. So this takes a Lubin-Tate group and gives you some kind of a graded formal group of additive type. And there's a slide here which says that this is, if you want to extend this stuff in terms of grading, this is just like what happens in terms of p-adically completed K-theory, where you have Adams operations which multiply the elements of higher or the beta by some power of some character, and you have to invert that character to make this group act on the graded theory as well. So that's what this slide is about, and I'm going to skip it. So what I'm saying now is that you have your Lubin-Tate group here. It's sort of additivization here. I'm taking spectra, so I'm making things work backwards. And over here, damn. Where did this slide come from? I missed it. This is the graded formal group. Anyway. Okay, here we are. This is the additivized Lubin-Tate group. This is the this is the formal group of THH of this big field. They're both additive, they're both groups of additive type, so there's an isomorphism between them. So you can express this a map between the formal groups as a map which sorry?
The space bar will switch slides for you.
I might.
He's saying you can use the space bar to switch slides.
Oh. I'm not sure I can even do that. I'm sorry. This is a little tricky. This omega to gamma here is a little confusing because W goes to pi 0 of V. So this is really a multiplication by pi 0. And the map on the coordinate is this exponential for this guy, followed by the inverse by the logarithm for the other guy. With a little unit thrown in here, which is really the key gadget. So really, I'm just going from one formal group to the other, both additive, and then I'm putting in a little piece of machinery that has some tricky properties. And that piece of machinery is the key to this equivariant stuff. Now, what I'm going to I'm out of time, so I'm going to try to skip stuff to say something about what the real issue is. The strong theorem of Morrow and of Schulze-Abat and Morrow identifies these things in terms of the symmetric algebra on the Tate module of the Kähler differentials of the perfective field in question. And what I'm talking about today is really about a calculation of that group. And so the key to that calculation is some futzing around with these Kähler differentials for these fields. And I claim that this follows from some generalizations, from a generalization of some work of Fontaine in '82. Which identifies these things in terms of Tate modules. In terms of Tate modules of formal groups. And in particular, when you start comparing these Tate modules, you find that the generator of one goes to a certain multiple of a power of the other. I put this thing here because if you look at the literature, this P0, pi 0 inverse runs through it like this sort of thread, which you can't figure out where it's coming from. And I think it's sort of the argument which I'm not showing you sort of clarifies that. Anyway, it turns out that this unit, which comes in here, reconciles the action of the Galois group on here, which is very small, with the action of the Galois group here, which is very big, and that the Galois group acts by multiplication of a ratio of these two sort of cyclotomic characters. This element U lies in the completion of this field, not necessarily in the field itself. So the equivariance is, once you know this about this little element, is straightforward. And I've got some things in the slides which I won't go through, telling you about this construction of Fontaine, but which is very interesting. It's based on this exact sequence. This is a little bit of the rest of the argument. The last stage says that there's this thing called the Schneider-Teitelbaum dual of Schneider-Teitelbaum version of the Lubin-Tate group, which is a p-adic analytic group. And I think this will just take me a second. I want to draw attention to this thing. There's something called the Tate module of the dual of the formal group, which is, I think topologists will recognize this, at least maybe Steve and Doug and Haynes will. Maybe not in that notation. Anyway, it gives you a map from the Lubin-Tate group, the group of points of the Lubin-Tate group, to the Pontryagin dual of the p-divisible dual, the double dual of the Tate module, and gives you this thing. So, thank you. I'll send you the notes if you want.
Any questions?
Can you summarize the main philosophical point that you're trying to come across? I got a little distracted, but
Yeah, I skip. Well, okay. Let me see if there was a place where I said something about that on there. If I can get back to it. I'm claiming that I can maybe it would be better if I just write this. So you got mu, you've got this map to THH of this big field, and I'm claiming that this factors through what I would like to think of was the sort of a lift of these mod p k theories. So this is supposed to be some theory which applied to CP infinity actually is the Lubin-Tate group for the field L. Okay, so and if you reduce it mod p, you get one of these KNs. So these things are, who knows? But they're sort of there on the formal group level. And you can make, from this you can make, well, so these things are associated to Lubin-Tate groups. These things are associated to these rigid analytic versions of Lubin-Tate groups. That's basically the. I take this. I take this as a credibility argument for the interest and existence of these things. You're going to have to yell because I can't hear.
These Adams operations that you constructed, are they supposed to be connected to the units inside the ramified rings of integers that sit
Yeah.
in the Morava stabilizer?
Yeah. The classical KNs have these division algebras, units of division algebras as operations. Sitting inside those division algebras, you have these sort of maximal toruses. And I'm saying that those maximal toruses, which are unit rings in these local fields, lifts to operations on the Lubin-Tate groups. That's sort of what the Lubin-Tate groups are supposed to do.
Can you put it on the slide? One slide?
One slide before this?
I think it's 2 slides forward.
Forward?
The slide just before that.
Oh, I'm sorry. Which way am I going? I'm sorry. One more? Sorry?
Anyway, what I want to ask before section, on the slide before section 3.3, you have some spectra that are probably local with respect to the Johnson-Wilson spectrum. And so when you smash that with the type N spectrum and then take stable homotopy groups, what is the cardinality? Is that typically going to be uncountable also?
Can you find that slide? That one?
Yeah.
That one.
Well, so some of your spectra, you would like for them to be continuous G spectra for an appropriate G.
Not for the whole division algebra.
Okay.
Just for the commutative, just for the multiplicative group of this local field.
Okay.
I think they are continuous, if that's what.
Yeah. Are any of them local with so suppose you're at a height n.
Uh-huh.
Are any of them local with respect to the Johnson-Wilson spectrum of height n?
Let's talk after.